In this video, we'll start talking about Lecture 0, which is a review of correlation. So, let's get started. Recall from your previous coursework that when we're looking at data analysis with two different groups of continuous variables, we typically use a t-test. So we may have a situation like this. In this situation, if we're looking to compare if the average of group A is different than the average of group B, this is when our t-test would be most appropriate. Sometimes though, instead of looking for differences between groups, we want to determine if the values, if they're associated between each row in the different groups, are related to one another. That is, we want to see if there is a correlation between the values given in group 1 and group 2. Correlation exists between two values when the values are associated with one another. Note that in this particular case with correlation, we're talking about linear association, and we can add that into our definition here. Also note that when we're talking about linear right now, we are thinking of having a line, but at a later time in the course, that definition of linear is going to mean something completely different. There are a couple of different ways that we can classify correlations. First, we can look at whether it has a positive or negative sign in the correlation. A negative sign would imply that as x increases, or as the first continuous variable increases, the second continuous variable decreases. So as one variable increases, the other variable decreases. In a visual form, the line that this would make would start at the top left and end at the bottom right. We can also have a positive relationship that says as the first variable increases, the second variable also increases. Visually, this would have a picture that starts at the bottom left and ends at the top right. In addition to the sign, we can look at the strength of the relationship. So values that are closer to a line, on average, form a stronger relationship and have a higher correlation. So if values group very closely to a line, then this typically will have a strong correlation. Values that are further from a line, on average, will form a weaker relationship. Smaller correlation. Note that when I'm saying bigger and smaller correlation here, this is the absolute value of the correlation. That's because we can have strong negative relationships and strong positive relationships. We can also have weak or small negative relationships and small positive relationships. So when we talk about strength, this means the size of the number, not whether it's positive or negative. And when we talk about sign, we're looking at the positive and negative aspect, not whether or not the number is big. Quickly, let's look at a few visual representations of some potential small, medium, and large correlations with a variety of different signs. On our digital blackboard here, I'm going to pull up some graph paper, and let's draw out a couple of these. So I'm just going to make a small axis with an x and a y axis, and then look at a plot of a few different dots, and of course yours don't have to match exactly with mine, it's the general idea. So our little line that's coming through here is kind of coming right through there. This would indicate a relatively strong relationship because the values tend to be clustered close to the line. Think about how far away they could be from the line. These tend to be right around it. This also tends to be a positive relationship. So a strong positive relationship is what this graph would indicate. In a second graph, let's draw a negative relationship, and I'll start by drawing this kind of center line that I want to cluster my points around. So this is going to be a negative relationship, I know ahead of time, because if I cluster points around here, the points are going to be clustered moving down this line. So they're going to be coming down from the top left to the bottom right. That's my negative relationship. And if you think about this, as x goes up, the y values start from high and go to low as x increases. Now if we wanted a moderate or a weaker relationship, our points are going to be further away from the line. Typically, if you can tell that it's a correlation, then it's going to be at least a moderate strength. So we'll call this a moderate negative correlation. Let's look at a couple more. Now let's do one with no relationship. No relationship just means that the dots are going to appear at random on the graph so that there's no line that goes through them. So I'm going to say no linear relationship. Of course, there doesn't appear to be a nonlinear relationship there either. And we can also have something like this, where let's say we actually have a really strong relationship. So we can clearly see this is very clearly quadratic. But we still have no linear relationship. So because of this, we get that same definition of no linear relationship on both one with no apparent relationship at all and one with a very clear relationship, but a relationship that isn't particularly linear. We'll start by talking about the Pearson correlation coefficient. The Pearson correlation you can think of as the regular correlation and measures the linear strength between x and y. Again, these are two continuous variables. The linear component is actually really important here. As we demonstrated in our picture, we're going to see some graphics where there's a very clear relationship between x and y, but that relationship isn't linear. And in this particular case, the Pearson correlation wouldn't actually do much with that. Now, again, I keep saying this, we'll write it in, but we need both x and y to be continuous variables. Just remember your definition of a continuous variable, that is, there's always an option. Now, very practically here, definition of continuous, there's always an option in between any two numbers. So between 1 and 2, there's 1.5. Between 1 and 1.5, there's 1.25. And if you can do that ad infinitum, then the variable is continuous. Practically, though, we just need it to have lots of numbers. So it's got to be numeric, and we need the values to be a lot of numbers. So something like, let's say, weight, where if you're asked about your weight for your driver's license, you're not going to tell them 135.258 pounds. You're going to tell them 135 pounds. What you may do in that case is treat all of those variables, even though practically there's not going to be anybody who has a number between 135 pounds and 136 pounds. And so mathematically, that would be a discrete number. We often treat those as continuous, but it's important to realize that that is a deviation from the requirement of a correlation. Correlation properly should have those continuous values, so we need to be careful when we make those deviations. We can calculate the Pearson coefficient with a somewhat yucky looking equation, but the letter that we use to represent the Pearson coefficient is R for the sample and rho for the population. Just like in your previous statistics courses, we had X bar for the sample mean and mu for the population mean. In Pearson, for Pearson's correlation coefficient, we have the same. Now I'm going to go on and write out the formula. And in fact, there are going to be two formulas here. The first is the traditional formula for the sample Pearson's correlation coefficient. That's going to be your sample size times the sum of xy minus the sum of x times the sum of y, divided by, now note that there's two square roots in the denominator, the square root of n times the sum of x squared minus the sum of x quantity squared times the square root of n times the sum of y squared minus the sum of y quantity squared. Now another way you can do this is if you translate x and y to z-scores. If you remember, a z-score takes each x value, subtracts the mean, and divides by the standard deviation. For every x value, that gives you the z sub x for that particular x value, and the z sub y for that particular y value. If you find the z-scores for the x values, the z-scores the y values separately, and then multiply them together, add them all up, and divide by n minus 1. That also is a way in which you can find the Pearson correlation coefficient. Let's talk about some properties of the Pearson correlation coefficient. First off, the Pearson correlation coefficient is between -1 and 1, where -1 and 1 indicate a perfect or a maximum strength relationship. You can think about this in that visual by if we had our line, all of the dots literally fall along the line. There's no movement. You can't even see the dots because they are directly overlapping the line at all points. That would be a positive 1 if it were a positive relationship line. It would be a -1 if it were a negative relationship line. If the values of any variable are scaled differently, think of kilometers to meters, different scales of variables. The Pearson's correlation coefficient doesn't change. This property is called scale invariance and is very handy. What that means is, let's say you did a correlation between height and weight in metric units and I did them in imperial units. Our correlations between height and weight should be exactly the same, except for rounding error when we switch back and forth between those different scales. So this is a very, very handy property of the correlation coefficient. Another handy property is if you swap x and y, so that is, you take your independent variable x and you list it as your dependent variable y, and then you switch y and make it x, the Pearson's correlation coefficient still doesn't change. Now note that R, recall, measures linear relationship, and only linear relationship. As we've mentioned before, it requires continuous variables. And one thing that we haven't discussed yet is it is sensitive to outliers. That is, if we have a point that falls very, very far off of this particular line, then the R squared value is going to struggle with that. Or excuse me, the R value is going to struggle with that. It's going to be thrown off by that single point. Now quickly, let's do an example. So what I'm going to do is I'm going to put up a data set here, and then we'll follow along in determining how we would compute the Pearson correlation coefficient. First, after entering my x and my y data, I'm going to need to calculate x squared, y squared, and xy just from looking at my equation, knowing that I'm going to need x squared and to add all those up, my y squared and to add all of those up, and then my x times y values. I literally find these values by squaring everything in the x column. So 5 squared is 25, and so on. Go on and fill out the rest of this table on your own as you're taking notes. After the table's been completed, you can go to the bottom of the table and write the sums in each of the columns. So for this column, I'm going to add up everything that's in x. The sum of x is going to be 24 in this particular case. I'm also going to do this for the rest of the columns. Once I have these sums written out, I can go on and begin doing my calculation. First, I'm going to copy and paste my initial equation and start to fill in these different components based on the values that I just found. So, for n, my sample size, I have 1, 2, 3, 4, 5 different observations. N is going to be 5. The sum of x times y, well, I just found x times y, and then the sum of that is 159. So I simply copy and paste 159 in the correct location. On your own, go on and fill out the rest of this equation, copying and pasting the appropriate elements in for their equation counterparts. After you've entered in all the appropriate numbers, you can go on and solve the equation. On my calculator, I get that the correlation between x and y is 0.795. We'll be using R in this class, and the command for calculating the correlation between x and y, two vectors in R, is lowercase c cor, then the vector x and the vector y. Checking that by typing in this data, you can confirm that this is the answer to the degree of rounding that we do in our hand calculations. Now, let's try doing the same example but with the z-scores. So, I'm going to go ahead and grab the table from above. Then I'm going to create columns for z sub x, z sub y, and z sub x times z sub y. Note that in copying my information from the above, all of my x values and their sums still say the same. For the z sub x value, I need to take each of the x values and subtract from it its mean. So I would find the mean of the x values, which would be 24 divided by 5, or 4.8. I would subtract that from each of the values. So let's write our equation here, x minus x bar divided by s, our standard deviation, and use this equation to calculate each of my z-scores. In this particular case, after finding these values, I get 0.24 for my first x value. On your own, feel free to go on, calculate the mean of x, subtract the mean of x from all of the x values, and then find the standard deviation of x, and divide that difference by the standard deviation for each of the values. After you're done, go on and play the video and double check your work. Here you can see my completed table, and pause and check your work if you'd like. The next step after this table has been completed is to calculate the sums. Now, a unique aspect of z-scores is when you calculate z-scores for a particular population, because z-scores do what's called centering the variable, or subtracting the mean from each value, a concept that we'll come back to later in this course. The sum for any given z-score will always be 0. However, when we multiply two z-scores together, their sum isn't necessarily 0. In this case, the sum is 3.18. Copying our equation from above, we'll implement the same procedure that we did last time. We'll start with the equation, and then we'll fill out each of the different components. N, being 5, is a value that we've already found earlier. The sum of z sub x times z sub y is the quantity that we just calculated as 3.18. Taking 3.18 and dividing by 4 leaves us with the exact same value that we found above, r equals 0.795, to the degree of rounding that we're able to do. Note that here the z-scores actually extend much further than 2 digits. I just wrote 2 digits so that it makes it easier to type in my notes. You can follow along by calculating these values in R if you'd like to double check your work as well. In R, the the function for finding the mean is just mean, and the function for finding standard deviation is SD. You can see the Intro to R notes for more reminders of these basic functions in R. This has been our first lecture on correlation. In the next lecture, we'll move beyond simply calculating correlation to how do we perform statistical tests of correlation.